Okay, have a look at page 21. This is on June 17, P42. In your current question, you have an electron that has a charge of -q and mass m. It is accelerated from rest in a vacuum through a potential difference of v. Show that the momentum p of the accelerated electron is given by this equation here. P is equals to square root 2 mqv. So say this one is your vacuum. Right now, you have an electron that is at rest. This because they say it's accelerated from rest. So this one is at rest. Okay, so you accelerate from rest in a vacuum through a potential difference. So you can assume that throughout this region of your vacuum, you already have a potential difference, a PD of V. Okay, so you apply a potential difference. This electron that was originally at rest will now start to accelerate towards the other end here. Okay, it will now move towards this side. It is now accelerating. Okay, so it is accelerating. Once it reaches this end here, it must have a certain speed already. Okay, so what you're interested to know is what happens when your electron is being accelerated through your PD here. You could say that whatever work that you do has been used to increase the KE of your electron. And then for work done in an electric field, this one here can be thought of as work done on charge in an electric field. So what you learned from the electric field chapter before this is that if you want to find out the work done on the charge inside an electric field, you could use charge times potential difference. Okay, so work done here is QV. It's now equals to my change in KE. My change in KE here is really just half mv squared minus 0. Okay, this part here, at the end, I have a KE because I have a certain speed. This one, I have KE equals to half mv squared. But this part here, when I was at rest, my KE is 0. So it's half mv squared minus 0. Eventually, you will get QV equals to half mv squared. All right, so that is for this particular part here. Now for the subsequent part of it, it probably will be better if I go and do another different working here for you, because you want to relate to momentum, isn't it? You could say something like this. Since momentum is mv, and then velocity is equals to p over m, what you can do from there is something like this. This one I'll just write a working somewhere else. From QV equals to half mv squared, I'll just write it here. From QV equals to half mv squared, you can say that it's QV equals to half mv times v. And then since p is equals to mv and v is equals to p over m, you can subsequently say as something like this, where you say it's QV equals to half p times p over m. Then after that, eventually you will get p squared equals to mqv. Therefore, p is equals to square root of 2mqv. Okay, this derivation is much easier to understand compared to the one that I originally written. Okay, so this one is your derivation here. Yeah, when you do your questions, just be careful a bit about the v that you use. There are two different v's here in your equation. This v is for velocity, whereas this v is for PD. Okay, try to write them so that they are different from each other. Otherwise, you might end up cancelling them off accidentally without knowing. Okay, then after that, you move on to V. The potential difference V through which the electron is accelerated is 120 volts. State what is meant by the de Broglie wavelength. So the de Broglie wavelength is just simply the wavelength associated with a moving particle. Okay, so you mentioned is wavelength is one mark. You say that it's associated with a moving particle is another mark. Okay, this is what the de Broglie wavelength actually is. And then from there, they want you to calculate out your de Broglie wavelength of the electron, you use your de Broglie wavelength equation. Lambda is h over p. Okay, and here, although you do not know the momentum directly, you did something related to it in the earlier part of the question, where you say that momentum is square root 2 mqv. So you replace it with 2 mqv, square root 2 mqv. Then after that, all you just need to do is you substitute in all the values. Your Planck constant is the usual 6.63 times 10 power minus 34. And then after that is divided by 2, multiplied with 9.11 times 10 power minus 31. Because this one is an electron, you therefore must use mass of electron. Okay. And then after that, your Q obviously will be charge of electron. Okay, so this Q is charge of electron. You need to be able to deduce what is the mass and what's the charge from the fact that they say it's an electron. So the PD they did tell you is 120 volts from this part here above. So just sum in the value for your voltage and don't forget to square root it. You will eventually get your wavelength as 1.12 times 10 power minus 10 meter. Okay, so that is for this particular part of your question. Okay, then that one is done. Then we move on to part C. Okay, so you then move on to part C. Now, in part C, they mentioned that the separation of the copper atoms in a copper crystal is approximately 2 times 10 power minus 10 meter. By reference to the answer that you have in B2, which is the one that you just found here, suggest whether electron diffraction would be observed by using a beam of electrons that have been accelerated to a potential difference of 120 volts and are then incident on a thin copper crystal. So the one that was described to you inside your notes was using a thin graphite film. But this one, they're saying they want to use a copper crystal instead. So they want to know whether would you be able to see the same electron diffraction pattern as you would if you were to use a thin graphite film. So one of the things that I mentioned to you just now is that if you want to observe the diffraction pattern, you need to have significant diffraction. The significant diffraction only occurs when wavelength is comparable to your atom separation. Okay. So since the wavelength in B2, which is this one, is comparable to 2 times 10 power minus 10, therefore your electron diffraction occurs. Okay, so what do we mean by comparable? This one here, what it meant is that the wavelength and separation have same order of magnitude. In other words, same power of 10. Okay, the separation of copper atoms is 10 power minus 10. The wavelength is also times 10 power minus 10. So they're actually considered to be comparable here. That's the reason why I said wavelength is comparable to this. Therefore, your electron diffraction can occur. Okay, so that's for this particular part. Okay, so if that is okay, then you move on to page 28. Let me just clear this thing up and then move on to page 28. Okay, so page 28 is on November 18, P41. All right. So this one I think is a simple calculation question. So you have a stationary isolated nucleus that emits gamma ray photon of energy 0.51 mega eV. State what is meant by a photon. A photon, as before, is just a packet of energy of electromagnetic radiation. We can actually just skip this one. So for B, for the gamma ray photon, calculate its wavelength. So you want to calculate out the wavelength of the photon. Okay. So for photon specifically, when you want to talk about its wavelength, it's always going to be E equals to Hc over lambda. Okay. you don't use the de Broglie wavelength straight away here. Because you already know that this is a photon and you want to calculate out its wavelength and you know the energy, you can actually just use this equation straight. So the energy is 0.51 mega eV. So times 10 power 6 to change it from mega to change out the mega. Then multiply with 1.6 times 10 power minus 19. Then multiply with your standard constants of H and C. Divide by your wavelength. Your wavelength will be 2.44 times 10 power minus 2 meter. Okay. So only after that do you use your de Broglie wavelength, because this time they ask you about the momentum. So when it comes to the momentum part, you use your de Broglie wavelength equals to H over P. P is Planck constant divided by the wavelength you've just found. Sub in the values of Planck constant and the wavelength that you just found, your momentum will eventually be 2.72 times 10 power minus 22 Newton second. Okay, so this is a pretty standard question. Okay, next one should be page 14. All right, so if you're okay with that, let me just go on to page 14. Right, so if you then move on to page 14, all right, this one is November 16 P42. Okay, so let's have a look at this one. Okay, so for the first part of the question, state an effect, one in each case that provides evidence for the wave nature of a particle. So what observation, what phenomenon that you know so far provides you evidence that a particle can behave as a wave? So we just went through that. That one is actually electron diffraction. Electron diffraction gives you proof that a particle can behave as a wave. And then for the second part, what phenomenon or what have you learned so far that tells you about the particulate nature of electromagnetic radiation? What have you learned so far that tells you that wave can behave as a particle? So the one that you've just learned 2 lessons ago is that photoelectric effect gives you evidence that wave can behave as a particle. Okay, so these 2 observations are really important. These 2 phenomena are really important because they give you particular evidence that wave can behave as particle and particle can behave as a wave. Okay, so these 2 are the most common examples to use. Now, if you then move on to part B, you have 4 electron energy levels in an isolated atom are shown. For an emission spectrum associated with these levels, on the figure, mark and arrow the transition that gives rise to the shortest wavelength. Okay, so since this one is an emission spectrum, I mentioned to you the arrow should be drawn downwards. Okay, so you want to draw the arrow, you must draw it downwards. You want the transition that gives you the shortest wavelength. So this one, you can actually say that E is hc over lambda. E is proportional to wavelength. If your lambda is minimum, your E is maximum. So this one must have largest transition between energy levels. So here you would need to draw from here to here, because this one will give you the largest transition between the energy levels. This one gives you largest E, shortest wavelength. Okay, and then from there, show that the wavelength, let me clear this thing off, show that the wavelength of the transition that you just marked out is 4.35 times 10 power minus 35. 4.35 times 10 power minus 7 meter. So your transition is between 0.54 to 3.4. You can just take the difference between them and ignore the negative. In my workings here, I actually included the negatives. Negative 0.54 minus negative 3.4. You actually don't need to bother about that. Just take the magnitudes, find the difference. You will get the value as 2.86 eV. Okay, so you want to find out the wavelength, just use the standard E equals to hc over lambda. Sub in your energy. remember to change to joules, plug in your constants, divide by your wavelength. Eventually, you get 4.35 times 10 power minus 37. Sorry, 4.35 times 10 power minus 7 meter. Okay, so this one is okay. And the last part here is again on de Broglie wavelength. State what is meant by the de Broglie wavelength. It is just simply the wavelength associated with a particle that is moving. That's all there is to it. And then in part 2, calculate the speed of an electron having a de Broglie wavelength equal to your wavelength in B2. So you want to find out the speed of your electron with the de Broglie wavelength that you just found in B2. So you need to use your de Broglie equation. Lambda is h over p, but your p you need to expand it to become mv because you want to find out the speed here. Okay, you want to find out what's v. All right, so v is going to be h over m lambda. V, sub in all the equations, sub in all the values, Planck constant, mass of electron, and then your de Broglie wavelength. You will get your final answer as 1.67 times 10 power 3 meter per second. Okay, so that one is for this question. All right. Okay, so if you just look at page 23, this is November 27 P42. There's this one last discussion I want to go through with you. So this one involves graph drawing apart from calculations. That's all you've been doing so far. Now, in this question, you have a metal surface that's illuminated with light of a single wavelength lambda. On the figure below, sketch the variation with lambda of the maximum kinetic energy Emax of the electrons emitted from the surface. On your graph, mark with symbol lambda naught the threshold wavelength. Now, the question here is actually describing to you your photoelectric effect. Based on what you've just read here, it's actually describing your photoelectric effect or a photoelectric emission, where you have a metal surface, a photon is incident on the metal surface, which subsequently cause an electron to be emitted with a certain kinetic energy. Let's just call this kinetic energy max. Okay, so the ones that you are very used to doing when using photoelectric equation was that you say Hc over lambda equals to Ke max plus your wavelength, such that Ke max is equals to Hc over 1 lambda, Hc times 1 over lambda minus phi. Okay, if you were to then equate this to the equation of a straight line, what you would have normally said is that if you plot a graph of, say, Ke max versus 1 over lambda, you will get a straight line graph with negative y-intercept. Okay, this one here, you will see that y-axis is actually Ke max, x-axis is actually 1 over lambda, your gradient is actually Hc, and your y-intercept is going to be negative 5. Okay, so you get a straight line with positive gradient and negative y-intercept. This is the graph that you expect to see. But the graph that you're being asked to draw here is Ke max versus lambda. It's a completely different graph. Okay, so how do you know that the graph shape is like this in the first place? So again, you kind of use back the photoelectric effect equation where you get something like this. I'm just going to use back the one that I have here where I say that Hc over lambda equals to Ke max plus phi, such that Ke max is equals to Hc over lambda minus phi. All right. So from looking at this equation itself, you could come to one conclusion saying that KE max is actually going to be inversely proportional to wavelength. If you just consider this portion itself, okay, KE max is inversely proportional to your wavelength. So that if you were to draw a graph of KE max versus versus lambda, if you were to draw a graph of KE max versus lambda, let me just try and find the words, the correct color here. If you were to draw a graph of KE max versus lambda, it should give you a straight line, it should give you an exponential curve like this, where you have asymptotes at both sides. So here, you expect to see asymptotes. If based on this equation itself, okay, you expect to see asymptotes. They don't cross the axis. The y-axis doesn't cross, the x-axis doesn't cross. You're just looking at this relation. Now, in the first place, why do I know it's going to be like this? This one is something that you have learned from maths before. If I tell you y is inversely proportional to x, straight away you will tell me that you plot a graph of y versus x, it's going to be something like this, right? You're applying that same reasoning here, okay? Now, let's just take this concept a bit further. Notice that your equation actually has this minus lambda here. If you consider this whole equation now, like this, where you say that it is KE max 1 over lambda minus phi, you consider what you've also learned in maths also. If you say that y inversely proportional to 1 over x, if you plot a graph of y versus x, it's going to give you an exponential decay curve like this. Let's consider another separate case where you say that y is inversely proportional to 1 over x minus a constant a. So if you try to then plot a graph out of it, of y versus x, let me try to draw it out here. If you try to plot a graph out of it of y versus x, it will still have an exponential curve pattern, but the entire graph will be shifted down by a. So it will be shifted down by a like this. So this entire graph have been shifted down by a. So this one here, the conclusion is that your graph shifts down by a. Okay, the graph shifts down by a. So it's a similar reasoning now when you're talking about your KE max versus lambda. Because you have a minus lambda here, you could say that your entire graph is actually going to be shifted downwards. All right, so that instead of having that red colored line there, it is now this pink colored line, because it has been shifted down by lambda. Sorry, it has been shifted down by phi. Okay, so your graph is shifted down by phi. Okay, so when you try to shift it down, you are going to end up with some sort of x-intercept here. If before you had an asymptote, now you actually have an actual x-intercept. Okay, so you want to find out what is your x-intercept, you have to relate to what you've learned before when it comes to threshold wavelength, because your question did ask you to indicate your threshold wavelength. What you remember from what I mentioned is that at threshold wavelength, lambda naught, KE max is 0. So your graph here is having 0 KE max here. Okay, because it's a graph of KE max versus lambda, your KE max is 0 right over here. So at the point where you have KE max equals to 0, this particular x-intercept here is really your lambda naught. Okay, so when you want to draw your graph, it will actually be this one. Okay, you actually have an x-intercept of x naught here, but this part here still remains as an asymptote. Okay, so this is how you draw your graph shape here. And then the last thing to note is for B, this one is talking about your de Broglie wavelength. A neutron is moving in a straight line with momentum p. The de Broglie wavelength associated with the neutron is lambda. On the figure below, sketch the variation with momentum p of the de Broglie wavelength. So this one will be very straightforward in the sense that you can straight away use your de Broglie wavelength equation when you say that lambda is equals, okay, maybe I should just draw it the other side here. Where you say that lambda is equals to h over p. H being constant here would mean that lambda is inversely proportional to p, which is same in form to x inversely, sorry, which is similar in form to y being inversely proportional to x. So if you now try to plot a graph of lambda versus p, it will just be this line here. Okay, but take note that in your current case here, these two must be asymptotes. Okay, so that is it for this particular question. All right. Now for the next question, you can look at page 22. This is actually November 2017 P41. So for this question here, the first part is asking you to state what is meant by a photon. A photon, as before, is a packet or quantum of energy of electromagnetic radiation. And in B, you have indium-123 is radioactive. A nucleus of indium-123 emits gamma ray photon of energy 1.1 mega eV. Determine for this gamma radiation the frequency. Since you have mention of energy as well as frequency here, you could use equation E equals to HF because gamma radiation in itself is a photon. So then right now, frequency is your photon energy divided by your Planck constant. So your photon energy is 1.1. Because it's in mega, you need to change the mega here by multiplying by 10 power 6. And you want to change the EV to joules, so you multiply with 1.6 times 10 power minus 19, before finally dividing everything out with your Planck constant, or 6.63 times 10 power minus 34. Your final answer should be 2.65 times 10 power 20 hertz. And then the next part wants you to find out the momentum of the photon. So when it comes to anything related to momentum calculation, the equation that would tend to come to mind is your de Broglie wavelength. Okay, so that right now, momentum is actually h over lambda, which is what is written over here. And another thing to note is that because you do not have the value for your wavelength, you have to find it out in a separate manner. If you recall the equation for wave being v equals to f lambda, in your case, you're talking about speed of light, so it's c equals to f lambda, plus wavelength is going to be speed of light divided by your frequency. So right now in your workings, you would have momentum equals to Planck constant divided by wavelength, and then your wavelength is actually speed of light divided by frequency. Eventually, your momentum expression will be P equals to HF over C. So from there, all you just need to do is to sub in all the relevant value for your Planck constant, for your frequency that you found from the part above here, and then divide it by the speed of light. Your final answer here would be 5.86 times 10 power minus 22 Newton second. For the last part, indium-123 nucleus is stationary before emission of the gamma ray photon. Use your answer in B2, which is the one here, to estimate the recoil speed of the nucleus after the emission of the photon. So let's just consider this. Initially, you had the indium-123 nucleus that was stationary. After a while, it started emitting a gamma ray photon. So this is what we might expect to see right now, where you have a gamma ray photon being emitted. It has a certain speed. It has a certain momentum. You already found out the momentum as being 5.86 times 10 power minus 22 Newton second. Okay, so you have a before and after case here, and you have momentum involved. So you would have to think about conservation of momentum here. So right now, this is the before case. This is the after case. Okay, so you try to apply conservation of momentum here. Conservation of momentum tells you that the sum of your initial momentum should be the same as the sum of your final momentum. This is what conservation of momentum is about. So right now, if you look at the total initial momentum before the emission of the photon, it should be 0 because you only have indium 123 nucleus there and it was stationary. And now, after the emission of the photon, if you apply conservation of momentum here, your total final momentum after the emission of the photon should also be 0. So right now, if your gamma ray photon has a momentum towards the right of this value, it follows that your indium 123 nucleus should also have a momentum equal and opposite to that of your photon. In other words, the momentum of your indium 123 nucleus is equal and opposite to the momentum of your gamma ray photon, so that the total final momentum after emission remains at 0, because you still want to obey conservation of momentum here. If the total initial momentum is 0, the total final momentum must also be 0. And the only way that your total final momentum could be 0 is if your momentum of nucleus is equal and opposite to the momentum of your gamma ray photon. So right now, you could actually say that the momentum of your nucleus being equal to the momentum of your gamma ray photon. From here, you expand out on the equation. If you recall that momentum is actually the product of mass times velocity, what is the mass of the nucleus of indium 123 here in the first place? You would actually need to take the nuclear number of 123 and then multiply with the unified atomic mass. The mass of your nucleus here is actually the nuclear number 123 multiplied with your unified atomic mass. And then after that, if you multiply it with your recoil speed, which is this one here, that one will give you your momentum of your nucleus. So it's 123U times V equals to the momentum of your gamma ray photon. So sub in the value of your unified atomic mass multiplied with the recoil speed, equate it to your gamma ray photon momentum. Eventually, you'll get your final answer as P equals to 2.87 times 10 power 3 meter per second. So this one would be your answer. Okay.